Okay, here we are at section 2, which is talking about the perpendicularity of a line and plane. So what does that mean, you ask? Well, we're going to have a definition of perpendicular lines and planes. And what it means is that if you have a line that is perpendicular to the plane, so for example in this diagram, line AG perpendicular to this whole plane, then it's going to be perpendicular to every line in that plane that passes through its foot. So that's why it's really important for us to know what the foot is. Okay, and then this right here, definition of perpendicular lines and planes, this is how we're going to write it as a reason in our proof. And we have to make sure that we add on this lines and planes part. We can't just say definition of perpendicular. Because if we do, then we're talking about two lines being perpendicular, creating a right angle. Okay, so in this example, if I knew, like it was given to me, that line AG is perpendicular to plane M, then I would be able to say that AG is perpendicular to line BD or segment BD, whatever you want to call it. I also know that AG is going to be perpendicular to BF, so this one, and it's also perpendicular to this entire line EC because EC passes through point B, which is the foot. And the reason that you would be able to say any one of these in a proof would be by the definition of perpendicular lines and planes. Okay? Now, you guys remember, hopefully, that every definition that we have, you can always write the converse of it, and that will also be true. But if you think about it, in this particular situation, we wouldn't want to have to do the converse of this definition, because it would be if a line is perpendicular to every line in the plane that passes through its foot, then it's perpendicular to the plane. I have a feeling that you don't want to have to prove that it's perpendicular to every single line, because there's actually an infinite number of lines that could potentially pass through point B. So they could go off this way and that way and all over the place. So that gets a little cumbersome. Nobody wants to do that. So what they did is they kind of reworked the converse into something that's more user-friendly, I guess. And they came up with Theorem 48, which says that if a line is perpendicular to only two distinct lines in the same plane, then it is perpendicular to the plane. So it cuts out the whole every line and reduces it down to just two lines. Okay, so when we go to write this in a proof, it says a line perpendicular to two lines in a plane implies perpendicular to the plane. Basically, it's the same thing, we just write it in symbols. So when you look at this example, if we know that AB is perpendicular to BC and BD, then we know that's enough for us to know that the line is perpendicular to the whole plane. Okay, and so that's what Theorem 48 is. We don't use this a whole lot. I mean, we do occasionally, but it's more common to use the definition of perpendicular lines and planes. So this one creeps up every once in a while. Okay, so let's put this to the proof. Let's see how we would do in a proof. Once again, when you look at this proof, it's going to seem very similar to a Chapter 3 proof. The only difference in this case is that we are going to use our new definition, because you see RO is perpendicular to the plane. But everything else is going to be very similar to Chapter 3. Okay, so they give us that circle O lies in plane N, and RO is perpendicular to the plane. And we're supposed to prove that RS and RT are congruent. So after stating the givens are given, we now know that RO, and mark it here, RO and OS are going to be perpendicular. And we also know that RO and OT are perpendicular. Okay? And so the reason that we can say that is by the definition of perpendicular lines and planes. So don't forget those three words right there. Okay, so next, now that we have perpendicular lines, now we can talk about having right angles. So angle ROS and angle ROT are right angles by our definition of perpendicular. Okay, so that's taken care of. What can we say about right angles? Well, right angles are congruent. I'm sure you already knew that. Already had that written down. All right, so let's see, what else do we have? Well, they gave us a circle. So in a circle, we know that the radii are congruent. So let's put that in. I'll go ahead and mark that up. So OS congruent to OT. Okay. So next, if we kind of look at what we're doing here, we're going to try to prove these triangles congruent. So we already have a side, we have an angle, we need to have this other side. So reflexive property tells us, ooh, that's a big circle. Okay, the reflexive property tells us that RO is congruent to RO. And now we have enough to say the triangles are congruent by side angle side. And then of course we can finish that up with CP/CTC to say RS is congruent to RT. Okay, so once again, everything very much like a Chapter 3 proof, only this statement right here that we had to use our definition of perpendicular lines and planes. So that's it, folks, for Chapter 6. Hopefully that wasn't too bad, and we will get ready to do Chapter 7. All right, see you later.